Well, adding some inductors in series is as if we're kind of just making our inductor longer and longer. So L equivalent is equal to L1 plus L2 plus L3. So this is analogous to resistors. Unlike capacitors, where you saw that the equivalent is kind of the opposite of resistors. And what about in parallel? Well, this is also equivalent to that for resistors. We have 1 over L1 plus 1 over L2 plus 1 over L3. All right, so here are the two equations that we came up with already. And from last time, we saw that we need time-changing fields for a capacitor to get voltage. And we have the same thing here, right? There's some time dependence here in order to get voltages. And so we're going to need, in our circuit, say if we have a battery, V in, we're going to need a switch of some kind, where I'm going to connect this. This is the simplest way that we can get something that changes in time. There are, of course, other ways. But here, say we have a resistor, and say we have an inductor. So if we close that switch, we'll start to have some time-changing currents and values. And also, what you might have noticed that I added a resistor here because we're never going to have just a perfect inductor with zero resistance and wires and everything just perfect. So we'll find that we can control things if we can control how much resistance there is in the, when we get to the time constant, we'll be able to see that. All right, so let's look at the case where the switch here is closed. The battery is connected to the resistor and the inductor. So in this case, we're going to get some currents that are going to be flowing. They're going to be increasing in time. We're going to get an increasing B field that goes along with that increasing current. And the current can change fast. We can see that right here, right? With 0 is where the switch closes. The current here is changing fast. So what's actually plotted here is the voltage across the resistor, but R is a fixed value. So as I changes, we can see the behavior here of how the current is changing over time. And so we can see the current here is increasing very quickly. And as it's increasing quickly, that means that back EMF is going to be large. It's going to want to resist that sudden change in the current. And we're going to get a large voltage drop across the inductor. All right, so I think starting from Maxwell's equations and B fields can help us to explain some of this behavior that we're seeing. So if the voltage here, this is for the inductor, starts out really high, in this case the highest it can go is that of the battery, then it looks like here the inductor looks like an open circuit. Right, so very briefly, right, when we close the switch, that inductor looks like an open circuit, but over time, as the current moves, the current is not changing as fast anymore. The charges are not migrating as much and not as energetic. So that current starts to go reach an equilibrium. Right, it's not changing really hardly at all anymore once you get out. This is versus time constants. And the voltage then also goes down to 0. So at this point, if the voltage is 0, in a long time, the inductor looks like a short circuit. So right now we're focusing on what's happening right at the beginning and right in the long time span. So right here, it looks like we have this battery that's connected to an open circuit where that inductor would be. And then on this side, once we get to the long time span, transients have gone away. It looks just like a short circuit. In that case, we just have R. And in a little bit later, actually next time, we're going to be exploring more about coming up with equations that what happens in between here. Now, if we were ever able to disconnect this battery, and instead we changed that switch so it's now the battery is shorted out. So I'm going to take that off. Now the battery is no longer connected. At this point, we're going to have the current is going to start decreasing, and it's changing quickly here, changing fast. It's reducing quickly. And so we're going to get a large voltage again across that resistor, but the polarity, it has an opposite polarity to what we saw before when the inductor was charging or increasing its magnetic field. And that's because it has an opposite polarity because it wants to resist the decreasing current. So before it wanted to resist the increasing current, now it wants to resist the decreasing current, which also means it wants to resist that decreasing B field. So eventually all this energy is going to discharge into the resistor. It'll be lost as heat. So the inductor L discharges into R. The L, I'll say energy, discharges into that resistor. So what's really important at this point is to know what does the inductor or a capacitor look like in the beginning, maybe when you close a switch. In this case, we don't have a switch. I'm going to go through an example here. And also, what do the inductor and capacitor look like after the circuit has been connected for a very long time? So in this case, we have a circuit. It's been connected for a very long time. So all the transients, all that charging or discharging or whatever is going on has already happened, and we reach steady state. And so now we want to know how much energy is stored in the capacitor and inductor. So go ahead and take a moment and look at this example, and then we'll go over it in just a minute.